All right, so day 3 of Unit 2 is the day that we start introducing proofs. We're not going to do a ton of proofs today. We're just going to kind of get our feet wet and take some baby steps so we can start learning what proofs look like and how we have to kind of think about them. But before we do that, we need to talk about some properties. So remember, when we are justifying things in this class, you're only allowed to use definitions, theorems, postulates, and properties, right? So today is the properties day. So for the whole year, we will be learning theorems, postulates, and definitions. But as far as properties go, today is the day, right? We're going to learn every single property that we use all year long today. Most of these properties you've heard of before or you've used and you just might not have known the name of them before. So we're just going to run through these really quick. So there's two types of property categories. There's properties of equality that of course we use with equal signs, typically when we're doing algebra work. And then we have properties of congruency. And of course those get used when you are using a congruent symbol and you're actually comparing, segments or angles to one another. Okay. So we're just going to start rolling through these properties of equality really quick. So you'll notice these first four, right? Addition, subtraction, multiplication, and division property. These are the ones we use every single day when we're solving algebra equations, right? You just might not have realized, what you were calling this, right? So the addition property, just like the other next three, basically says if I add a number to both sides of an equation, it's still equal. So this is what we do every time we solve an equation where we add. So for example, if I look at the equation x minus 3 equals 5, right? We all know that when we solve that, we're going to add 3 to both sides, right? In order to keep the equation balanced and to cancel out that 3, and we get the solution x equals 8. Well, in order to get x equals 8 or to justify the solution of x equals 8, we would say we used the addition property, right? Because we added 3 to both sides and kept it balanced, and that's how we got the solution. Okay, so that's the addition property. Of course, the subtraction property is the same, right? If I have to subtract a 3 from both sides to solve for x, right, that is the subtraction property. The multiplication property, right, is exactly what it sounds like. I'm just going to put a quick little example over here. Right, if we were to solve the equation, x divided by 2 equals 3, right, we know that the conclusion to that, right, it would be x equals 6 because we're multiplying by 2 on both sides of the equation. Now, I am going to, let's see, put a little box right here. I do want to make you aware that there is a difference between multiplication and the multiplication property. And what I mean by that is, let's say you have the equation 2 times 4x equals like 25. I'm just making up some numbers. The first thing that most of us would probably do in that equation is we would multiply the 2 times the 4x, right? And we would simplify that to 8x. But I just want to make you aware that that's not the multiplication property, right? The multiplication property is when I multiply both sides by the same number in order to solve for an x. And that's not what we did over here in this box, right? I just multiplied 2 times 4, right? I'm just doing the operation of multiplication. I'm not using the multiplication property. Okay, so I just want to make sure that we understand that there's a difference. So if you ever are just multiplying two numbers on the same side of an equal sign, then you're just multiplying, right? So you can literally just write I multiplied, or you can write operation of multiplication, right? And that's different than the multiplication property, right? And same goes for all the other ones. Sometimes people are like, well, I distributed. Well, you want to be careful because you technically didn't distribute, right? Because distribute means to send to more than one term. So we would have to have something like 4x minus 3 equals 25, right? That would be the distributive property because I'm actually multiplying multiple things by 2. So we'll talk about the distributive property in just a second, but I just don't want you to get confused there. All right, and then of course you have the division property, which again, we use this every single day when we solve equations like, 2x equals 10. Oh, I divide both sides by 2, right? So that the 2's cancel, but I do that to keep my equation balanced, and so I can make the conclusion that x equals 5, right? And I reach that conclusion because of the division property, okay? All right, so those are just our basic math properties there. The 3 highlighted in yellow here, they're super important, and they're highlighted for a reason, which I'll talk about here in just a few minutes. So I'm just going to run through these really quick. The reflexive property of equality basically just says that anything is equal to itself, which is kind of like, well, no kidding. Like, it almost seems useless, but it's really not. We use it all the time. So it could refer to, it could be like 5 equals 5 or x equals x. It could be the measure of angle 5 is equal to the measure of angle 5, right? So when we need to say that something is equal to itself, that means we're using the reflexive property of equality. I remember the difference between this and the others because, like, I think of reflective like a mirror, right? So if I'm reflecting A and A, right, that's like a mirror image of itself on both sides, right? So reflexive property is a reflection of itself. And then you have the symmetric property. The symmetric property just says that if A equals B, then B equals A, which essentially is just saying that we can flip-flop the 2 sides of an equation and it's still equal, which we all know. And this is, I'm going to kind of illustrate, this is the most common reason why we use the symmetric property. Let's see, let's say we have the equation 9 equals 3x. And I asked you to solve that. Well, most of y'all would say, oh, well, x equals 3, obviously, right? However, I don't want to write x equals 3 because, remember, proofs are baby steps. Like, you've got to prove every single tiny step of how you get to the solution of x equals 3. The reason I can't just write x equals 3 is because the x is not on the left side, right? So when I divide by 3 on both sides, I get 3 equals x, not x equals 3. And if my problem wants me to get the answer x equals 3, then I would actually have to take a step and switch the 2 sides of my equation around. So from here to here, I'm using the division property, but from here to here, I'm using the symmetric property to get it in the order that I want. Okay, so that's going to be the most likely scenario for us as how we're going to be using that, is really just to switch it around to get it in the right order. Okay. The last one is the transitive property. You've probably heard of this before. When I think of the transitive property, I think of a train, right? Like a bunch of train cars that are connected together like this, right? Well, of course, it's a train, so they're all connected. And that just helps me remember, because this says if A equals B and B equals C. Well, I've got this middleman, and I use that phrase a lot. It looks like everybody's equal to B, right? A is equal to B and C is equal to B. Well, if that's the case, then A and C have to be equal to each other. Okay, so basically if everybody's equal to the same thing, then everybody's equal to each other, right, is what the transitive property tells us. So again, I just remember that because I think of a train, like a train of cars. They're all connected, right? So they're all part of the same train. I don't know if that helps, but if it does, great. If not, just kind of throw it in the trash. All right, our next property is the substitution property. And we use this all the time, right? It basically just says if you know 2 things are equal, then you can substitute them in for one another, okay? So we do this a lot when we're checking our answers, right? When you get like x equals 5, we can check our answer by going back to the original problem, and everywhere I see an x, I can substitute a 5 and then work it out and see if it's good, right? And so we do this a lot anyway, but we're going to be doing a lot of substitution because we're going to be finding things that are equal, right? And we want to substitute them in so we can advance the problem and continue on, right? So we'll be using the substitution property a lot. The last property is the distributive property, and you guys all know and love the distributive property, right? It says if I have a value that is multiplied by a binomial or trinomial or just any type of polynomial that's more than one term, then I can multiply that through and get rid of my parentheses, okay? The last one is not technically a property, but I went ahead and put it on this list. This is combining like terms, which we all know that a lot of times when we solve equations, we have to combine like terms. And so anytime you do that in a proof, you're allowed to just write that as your reason, right? You could also write the operation of addition if you want in place of combining like terms, and that would be appropriate as well. But anytime you do combining like terms, you can just write that. And I abbreviate that as CLT, so I don't have to write combined like terms out all the time. All right, so now we're going to play a little game called Name That Property, right? So remember, look at all these. These are all written as if-thens, which is what we talked about yesterday, right? And these are kind of like mini proofs almost, right? And so basically, if I'm given this, right, if I know 4x equals 20, then what allows me to conclude that x must equal 5? Well, hopefully you can see that we're just solving an algebra equation and we would be dividing by 4 on both sides. So my justification for that would be the division property. All right, this next one, this is the hardest one. So AB plus EF equals EF plus CD. Then how can I conclude that if I know this is true, how can I conclude that AB must equal CD? Now, most students' first response is they say the transitive property, which I totally kind of see how that looks like the transitive property, but it is not. And the reason why it's not the transitive property is because these plus signs, right? If you go back up here and look at the transitive property right here, there is not a plus sign to be found, right? The transitive property is a connection of equalities that connects three things together, okay? And there's no plus signs in that. If this said AB equals EF and EF equals CD, like that would be the transitive property, okay? But that's not what's happening here, so it does look a little confusing. So what you kind of need to ask yourself is, well, if this is my conclusion and I have an AB and a CD right here, then what went away? Right, so hopefully you can see from our hypothesis to our conclusion, all that happened was that the EFs disappeared. Well, in an algebra equation, how can I get these positive EFs to go away? Well, I can subtract them from both sides, and then my EFs cancel each other out. It's kind of like having an X on both sides of an equation or a 2 on each side, right? I would subtract it away and the term would disappear, and that's what's happening here. Right, so this is actually the subtraction property because all I'm doing to get from my hypothesis to my conclusion is I'm subtracting the same thing from both sides of an equation. All right, the next one, hopefully we can see that right away, right? We have parentheses to start and then we don't have parentheses anymore, right? And typically when that happens, that means we are using the distributive property. All right, and then moving on to the next one. If we have the equation 2x divided by 5 equals negative 20, then what allows me to say that 2x must equal negative 100? And again, it's all about analyzing what's not there anymore. And you can see that in my hypothesis, I have a fraction, and in my conclusion, I do not. So they've clearly done something to get rid of the fraction, and hopefully we can all see that that means that we have multiplied both sides by 5. So this would be the multiplication property working. And then this last one can also be a bit confusing because there's a lot going on. So I just want to kind of make sure we see what's happening. The hypothesis is very long. So it tells us two things. The measure of angle 1 is 30, and the measure of angle 1 plus the measure of angle 2 equals 90. So I've got two different things there. Then what allows me to conclude, right, that 30 plus the measure of angle 2 equals 90? Well, let's take a peek. This is the algebra equation. Oops, sorry, I'm trying to highlight. This is the algebra equation I have in my hypothesis, and this is the algebra equation I have in my conclusion. They're very similar, but what changed, right? And hopefully you can see that what changed from this guy to this guy, oh, sorry, there we go, is that I don't see the measure of angle 1 anymore. The measure of angle 1 has been replaced with a 30. Well, what allowed me to do that? Well, over here they told me that the angle 1 was equal to 30. So I replaced the angle 1 with a 30. And of course, a fancy word for replacement is substitution. So this would be an example of the substitution property. All right. I think I lost my, there we go. All right, so those are our properties of equality. They can only be used for equal signs. If you have a congruency symbol in your statement, then that means you're using a property of congruence. Okay, now you'll notice there's only 3 of them, and I'm hoping you also notice that they have the exact same names as the 3 yellow highlighted equality properties, which can get kind of confusing because now you have the same exact named properties in equality, and you also have them in congruency. So you have to make sure that you explain in your problems which one you're using. So you have to actually write of equality or of congruency. You don't have to do that for anybody else. Like you don't ever have to say like the addition property of equality. You can if you want to, but it's not necessary because there's no such thing as the addition property of congruency. Right, so the only ones you really have to worry about are those yellow highlighted ones. And I'm going to go ahead and highlight these in yellow too, just to kind of color code them. But they work, the properties are the exact same, however, it's just with congruency symbols. So now instead of algebra equations, you're using more of a geometry comparison between angles and segments. Right, so there's kind of an example for both of those in each of these categories. So I'm just going to fly through this really quick. So your reflexive property, of course, says that anything is congruent to itself. So segment AB is congruent to itself. Angle A is congruent to itself. That makes perfect sense. Okay. The symmetric property, remember, of equality says I can switch the 2 sides of my equation and they're still equal. Well, the symmetric property of congruence says the same thing. If I have a congruency statement, I can simply switch the sides and they're still congruent. And then we have the transitive property, right? And so that's going to look like the same thing. If AB is congruent to CD and CD is congruent to EF, then AB and EF must be congruent. Again, a lot of times I call that the middleman. Right? If you've got a middleman that everybody has in common, right, then he's connecting the first to the last, right? Just like a train, right? And so that's how we're getting that conclusion. And of course, it works the same way for angles, as you can see right below that. Okay. All right. This next pink box is super important. And again, a lot of this is kind of overwhelming at the beginning because we haven't worked with all this stuff yet, but we're going to be doing tons and tons of proofs together. So this is all going to make a lot more sense as we do some problems. So the definition of congruent, we defined that in Unit 1 when we talked about midpoint, right? So the definition of congruent is if things that are equal in length or measure, okay, or size or shape, right? Anything that's the same. So I have these 2 little pictures here of these islands, and I use these phrases a lot, which is why I put them in the notes, right? I talk a lot about the land of congruency and the land of equality. So you can never be you can't be in both places at once, is my point. So when you're working through a geometry proof or a geometry problem in general, sometimes you may start off in the land of equality, right? So you're like working with an algebra equation, but somewhere along the way, it's going to morph into a geometry problem and you're going to end up in the land of congruency. Okay, and you'll see what I'm talking about as we work through some problems. Maybe not today, but tomorrow and the next day. But you are allowed, you can't be in both places at once, but you are allowed to hop back and forth between the 2 lands. But there's a requirement, right? You just can't hop, right? You have to justify the hop. And the justification is the definition of congruent. So what I mean by that is, let's say I'm working a problem, a proof, and it says like the measure of angle A equals the measure of angle B. Well, clearly I'm in the land of equality because there's an equal sign and I'm talking about their measure, right? But what if somewhere down the line, I don't want to be talking about their measure anymore, and I want to tell you that the angles are congruent, right? And so I'm going to have to transform at some point and say that angle A is congruent to angle B. And you can do that, but again, you have to justify every step that you make. And if you want to make that transition, then the definition of congruent, right, is what you're going to be using to justify that jump from one land to another. Okay? And again, you're going to see in just a few minutes what I mean. And I'm actually going to make this a double arrow up here because it doesn't matter if I'm going from the land of equality to congruency or the land of congruency to the land of equality. We're still using definition of congruent in order to justify that move. Okay? All right, so bear with me. We'll see that in just a sec. So let's go play the name that property one more time. So if we look at A, it says if segment NK is congruent to BD, then segment BD is congruent to NK. Well, you'll notice absolutely nothing changed except we just switched sides, right? And hopefully if you're looking up here, right, that is the symmetric property of congruence. Now, you don't have to write of congruence if you don't want to. You can just put a congruency symbol after it. That's totally fine with me. But you do have to put the congruent symbol because if you don't tell me whether it's the symmetric property of equality versus congruency, I'm going to take a point off. Okay? All right, the next one, if angle R is congruent to T and T is congruent to P, then R is congruent to P. So hopefully you are thinking transitive property of congruence. There we go. And you can see that middleman, right? It's just a whole series of congruencies. Congruent, congruent, congruent. Right? There's no plus signs. There's no minus signs. It's just a big, long string of everybody congruent to everybody else. All right, the next one. If segment AB is congruent to segment CD, then the length of AB is equal to the length of CD. So this would be definition of congruent. Right, what I was just talking about right above with the two islands, right? The A, the B, the C, and the D. Nothing changed. The AB is still on the left. The CD is still on the right. The only difference between my hypothesis and my conclusion is one is in the land of congruency and one has switched over to the land of equality. Right, so that is definition of congruent. And then the very last one is the measure of angle 2 equals the measure of angle 3. So therefore, angle 2 must be congruent to angle 3. And so hopefully you're saying, well, that's also definition of congruent. Right? Because again, the 2 and the 3 are both still there. They're both on the same sides as they started on. The only difference is on the left, on the hypothesis, I was in the land of equality, and then I switched over and wrote it as a congruency statement. All right, so now for the fun part, right? Now we're going to start talking about proofs. So this right here is like the anatomy of a proof. There's a few different ways to write proofs. There's paragraph proofs, there's flowchart proofs, but in this class we mostly stick with 2-column proofs because it's just a really good way to organize your information. So it's called a 2-column proof clearly because there's 2 columns, right? The first column is your statements column, and then the second column is your reasons column. This is where you're going to be justifying everything. So notice I wrote right here, right? The only thing you're ever allowed to put in the reasons column is definitions, postulates, properties, and theorems that we've learned, right? And that's it, right? And so you are going to have to remember all these, right? You got to memorize all these names and you got to keep track of what they mean so that you can use them at any time during any proof, okay? Which is the hard part about geometry. The statements, these are statements that you're going to have to come up with on your own, right? And it's basically just a big long string of if-thens, which is really cool, right? So basically you're like, okay, well, if this is true, then this can be concluded. And then that new statement becomes your new if. So if that's true, then this must happen. And then this becomes your if. And you keep going and going and going until you prove what you're trying to get to. Now, how do you know what you're trying to get to? Well, every proof at the very top is going to have these 2 statements. You're going to have a given, right? And the given is your first clue. Remember, we're clue finders, right? So you have to start somewhere, right? If you're in a scavenger hunt, right, you just don't start walking around, right? You got to get a clue so you can figure out where to begin. Same thing with proofs. So the given is your first clue that's going to get the ball rolling, right? And then you have to take that given and you have to start making conclusions and more conclusions and more conclusions until you get to the proof statement, right? You're not done until you get what they want you to prove, right? And that'll be written right underneath your given. Okay. Sometimes there is a diagram in geometry. Most of the time, if it's a geometry proof, it's going to give you a diagram or a picture. And sometimes your clues come from your picture, right? The given is not your only clue, right? The pictures are going to be clues too. All right. Now, we're not going to be doing a lot of geometric proofs today. We're going to kind of just ease our way in, and we're going to start with algebra proofs. Now, today is the only day we're ever going to do algebra proofs, right? This has nothing to do with geometric proofs. This is just kind of allowing us to see the flow of a proof and how it kind of works, okay? So we're not going to be doing these anytime again past today. All right, so this is a very basic algebraic proof, right? But you can kind of see all the workings of it. So here's my given. I'm just going to highlight it actually. Here's my given statement, 4 minus half x equals 7 halves minus x. And they want me to prove x equals -1. Well, this is just solving an algebra equation, right? This is nothing. You do this every single day in math, right? So all we're doing is solving the algebra equation, and we know we're done when we get x equals -1. Now you'll notice in the proof here that this proof is partially filled in for you already in some spots. Personally, I hate this. I do not like when proofs are partially filled in. And that's because when proofs have been partially filled in like this, it totally pigeonholes you or leads you to thinking in a certain way. And it doesn't really allow you to find your own path in the proof, because all proofs do not have to look alike, right? And to be honest, the way that this proof right here is written, I would not solve the equation this way. Okay, so I don't like the partially filled in proofs because you're forced to follow somebody else's logic. So just kind of keep that in mind. Eventually we will kind of we'll lose the filled in stuff, thankfully. But for not right now, we're kind of putting that in there to just kind of help you along in the beginning. Okay, all right, so here we go. We're going to start with step 1. Well, notice what step 1 says. 4 minus 1/2 x equals 7 halves minus x. That looks familiar. That's the given. And of course, that's always the first statement, right? Because that's your first clue. So every single time you start writing a proof, your given is the number 1 box, right? And of course, your reason is, how do I know this? Because it was given to me, right? So you're just going to literally write the word given. So that's your first clue, and now you can start rolling, right? So this person clearly has chosen to multiply by 2 on both sides. Well, that seems logical because there's a lot of fractions, so that seems like a reasonable step to take. So the fact that we're multiplying by 2 on both sides, well, of course, that would be the multiplication property, right? So we're justifying the step after we do it, right? What can I do to my given? Oh, I can multiply by 2. What allows me to do that? The multiplication property tells me I can do that, okay? And now you'll notice that when I multiplied by the 2 on both sides, I didn't just go ahead and multiply by 2. And the reason I didn't do that is because these are binomials on each side. And so I know that after I multiply by 2 on both sides, I am going to have to distribute to get rid of those parentheses. I don't want to do that all in one step because technically the multiplication and the distribution would be 2 separate properties, and I've got to make sure that I split that up, right? You don't want to be doing 2 or 3 or 4 steps, you know, all in one line. Okay, so when we distribute, we're going to write down what we get, all right? So 8 minus x equals 7 minus 2x. All right, and so now we just keep going, right? What would the next step be? Now, regardless of what you would do next, this has already been partially filled in, so they've already done that for you. So you'll notice the minus x and the minus 2x are still there, right? So you can want to use your context clues here. So clearly, the new number is 1, Right, and how did we get that? Well, obviously we subtracted 7 from both sides of the equation. So if I'm subtracting 7, then I just use the subtraction property. All right, well, we did that, or they did that, so that they could get all their constants over to the left. Well, we know of solving equations that if we get all of our constants to the left, then we need to get all of our x's to the right. So my next move definitely has to be adding the x to the other side, which will give me 1 equals negative x. And they've already filled in, that is the addition property because we did add an x to each side, right? And we're getting oh so close to solving, right? We've got 1 equals negative x, so we clearly need to divide by -1 or multiply. I would take division or multiplication property here, since dividing and multiplying by a -1 gets you the same result. But I think most of us would probably write division property, so I'm going to go with that one. And then you might be thinking, well, we're done, right? Because I've solved for x. But remember, you're not done until your answer looks exactly like what the proof is. And the proof wants the x on the left, right? But the way we've chosen to solve it, or this person, right, the x is still on the right. So we need to switch it around, which requires an actual property. And hopefully you remember that the switching property is the symmetric property. And I need to make sure that I include the of equality because there's a congruency one too, right? And we want to make sure that we're not using the wrong theorem or the wrong property, sorry. All right, could we have done this a different way? Of course, right? I wouldn't have solved it this way. I would have gotten my x's to the left and my constants to the right, and then that would have saved me. Sorry. Ignore the door. That would have actually saved me a couple of steps. So all proofs can kind of be done in a different way if you're blank and you're doing it from scratch yourself. All right, so now we're going to up the difficulty just a tiny bit so you can kind of get an idea of what we're actually going to be working with when we do geometric proofs, okay? So I love these examples here. So notice there's lots of givens, which is awesome, right? The more givens, the better, right? Because the givens are your clues. So the more clues, usually the easier it's going to make it. So all of this are my given statements. And just for the sake, I'm going to go ahead and write them all down while I'm talking, right? And I'm going to give them each their own line. Now, some people like to use the givens as they need them. So maybe I only want to use the first 2 givens and I don't need the third one until like step 5. All right, so some people like to use the givens as needed and some people like to just write them all in at the very beginning and just get it over with. That's totally personal preference. And as we do more and more proofs in class and stuff, you will decide how you prefer to use and write your givens. I'm just going to go ahead for the sake of just beginnings and write them all up front. All right, so we've got k plus p equals 2m and p equals k and m equals 4r. But then remember, you don't want to just jump into your proof, right? You have to analyze what you want to prove, right? You have to know where you're going before you start, right? So don't just start doing stuff and, just magically expect to get to some random conclusion, right? We want to know what we're trying to prove. So we want to do a little bit of analysis here. Now, you don't have to write any of this down. I'm just want to try to train our brains and how we want to start thinking. So you'll notice in our given, my given contains a K, a P, it has M's in it, and an R. Right? So there's 4 different variables happening in all of that given information. But I only want to get to a proof statement that has K's and R's. Right? So that's something you need to pick up on. Right? If I only want K's and R's when I'm all done, well, does everybody see that means I need to get rid of my P's and M's? Right? Somewhere along the way in my proof over here, I have to eliminate the P's and M's, so I'm just left with a statement that K equals 4R. Okay? Now, what you don't want to do, don't just stare at the proof, right? You have to be brave and you have to be able to just jump in and try something. Find a connection, write it down, and just see where it takes you, right? You don't have to be perfect at proofs, right? Everyone's going to make mistakes. You're going to be erasing a lot, right? So it's okay that if you make a wrong move, just erase it and start over. It's not a big deal, right? But you just have to be brave enough to start something. Okay, so let's take a little peek at what's going on over here. I've got to get rid of my P's and my, what was I say? M's. P's and M's. All right, so again, there's so many ways you can do this proof, right? So how I see it may not be how you see it, and that's totally okay, right? So let's see. The first thing I notice is that I need to get rid of my P's, right? So I notice right away that P equals K is one of my clues. Well, if P equals K, that means wherever I see a P, I can substitute in a K. Well, and there's a P right there, right? So what I can do is on step 4, I can rewrite step 1, but I'm going to replace or substitute the P with a K. Now, don't add the K's together yet because that's 2 steps in 1. You have to do it one baby step at a time. Okay, so since I replaced the P with the K, that, of course, is the substitution property. Now, I'm going to do something every time I do the substitution property, just for Unit 2. I'll probably stop doing it later down the road, maybe, but I'm going to keep a little notation off to the side of what I've done, of like which line I substituted into which line. So in this case, I took line 2, right, and I substituted it into line 1. So I'm just going to put 2 and then like into, like with an arrow, 1. And you don't have to do that. That's not part of your grade by any means, but it is handy for you to do that. So that if you were to look back at your notes, you're not just like, where in the world did this come from? I have no idea what I substituted or where that statement even came from. So it's a nice way to just kind of keep track of your logic. Okay. All right. So now I have K plus K equals 2M. Now, if you want to, you can go ahead because clearly at some point I need to add those K's together. So if you want to do that right now, then that would be great. So I'm going to go ahead and do that. So 2K, because K plus K is 2 Ks. So 2K equals 2M. Okay. All right. Well, what did I do? Well, I combined like terms, right? K plus K, those are like terms. I added them. Or you can write the operation of addition, right? Because you just added 2 Ks together. That's fine too. All right. Well, let's see. I'm going to keep going off of this. If I have 2K equals 2M, I notice I have a 2 on both sides. So can't I get rid of the 2's and just write K equals M? Right, but what allowed me to get rid of the 2's? Well, I divided by 2 on both sides. So that would be the division property. So now, again, I always want to kind of revisit my analysis over here, right? So I'm not quite done, right? Because I need K equals 4R. So I only want K's and R's, and right now I have a K and an M. So I got to get that M out of there. So I'm going to go back up to all my clues, and I notice right here, luckily, that 4R is equal to M. So everywhere I see an M, I can substitute in a 4R. And that is going to do it, right? Because now I can write K equals, but instead of M, I'm substituting a 4R in its place. And that is what I was trying to get to. So I'm going to put a little happy face right here. So yay. Notice I didn't need step 8, right? You don't always have to use all of the lines. I usually put just enough or a little bit more. If you would have solved this a different way, maybe it would have taken you 8 steps. If you end up having to add a whole bunch of lines, like if you're like working on this and you're like on like line 15, I would pause, right? And I would go back because you're definitely making it harder than it needs to be. And you might want to erase and start over and try to start down another path. Okay, so this, of course, is the substitution property again. And again, I'm going to put that little notation of what I substituted. So I took, let's see, I took line 3 and I inserted it into line 6 for my substitution. All right, so again, I'm just kind of keeping track of that. And voila. We've just proven step by step that K has to equal 4R, right, by using all those wonderful clues that we were given. Awesome. Okay, there's another one of these. If you want to pause the video, you can and try to do it yourself. But again, please be aware, right? There's like 6 or plus ways that I can actually work this proof. You don't have to do it the same way I do. Okay, so I'm going to fly through this one a lot faster. So again, I'm going to go ahead and write down my givens. And let's see, what does that say? 6. Oh, that says 6A. There we go. All right, and then given, just to get them all in there. All right, and I'm trying to prove that C equals D. All right, so again, I'm going to do a little analysis. My given, has A's, B's, C's, and D's in it. But I only want C's and D's in my final answer, which means I got to get the A's and the B's out of there somewhere in the mix, right? So we're going to kind of tackle that one at a time. So let's see. Something that jumps out at me is that I know A equals 1/3 B. And then I see another A right here. Okay. And again, you might see something totally different. It's okay. I'm just noticing something and I'm going to take a leap. And I'm just going to try it and see where it takes me. Right? No pressure. Here we go. So let's see. That's going to be 6. And instead of times A, 1/3 B equals C. Okay. So I just used the substitution property. And again, I'm going to use my little clue so I don't get lost if I look back at this later. So I took step number 1 and I inserted it into step 3. Okay. Now, obviously, I don't want to leave this mess right here, this 6 times 1/3 business. So I'm going to go ahead and multiply those together, which is going to give me 2B equals C. And remember, that's just the operation of multiplication, or you can just write multiply if you want. Operation of multiplication. Do not write multiplication property because I did not do something to both sides of the equation to solve it. I just simply multiplied 6 times 1/3 on the left side, and that's it. All right, so I'm halfway there, right? I'm trying to get C's and D's, and I've got C's, but now I've got B's. So I need to get rid of the B's. Well, luckily for us, up here in step 2, they tell us that B is half of a D. So I can replace the B with a half D. So I'm going to write this as 2, and instead of B, I'm going to write half D equals C. Sorry, I lost my train of thought there. And so, of course, once again, that is the substitution property. Make sure you write out substitution. Do not abbreviate it sub because we can't tell the difference between like subtraction and substitution there. Let's see. What did we replace? We put in step 2 into step 5, right? That's our replacement. And then I can, of course, multiply the 2 times the 1/2, which is going to give us just 1. So that's going to end up giving us D equals C. So once again, that's the operation of multiplication. I'm going to cheat and totally copy and paste that. There we go. With this little wiggle right there. And I'm not quite done. I'm oh so close, right? But they want C equals D, not D equals C. So we are going to switch it around. And the only thing that allows me to do that is the symmetric property of equality. And you can just put an equal sign, but I definitely have to have that. Woo, all right. So if you pause the video, right, I hope you come back, right, and it's all done and you did that well. Now, again, yours doesn't have to look just like mine, right? Normally when I'm in the classroom, I see like 10 different variations of this proof, right? And they're all correct, right? But everyone just kind of took a different path. All right, we are going to do this one little quick geometric proof just so you can kind of see how this works. Okay, when we get to an actual geometry picture, notice the lovely diagram. All right, so we're going to start this the exact same way we do any other proof, right? We want to analyze, right? Here's my given. And we always put the given in the first box, right? And so I'm going to go ahead and write that AC equals AB plus AB given. Now this given is not nearly as lovely as having all three of these givens up here, right? Because these actually help me do something and they lead me to other clues and conclusions. This given, while it's helpful, it actually doesn't lead me to another conclusion. Okay, and this is going to happen sometimes where the given is an important piece of information, it just doesn't lead me to another piece of information. So when that happens, you're done with the given. It's not given up anymore. Okay, so you just are going to let it hang out there. Now, when you're done with your given, you still need another clue. So where are we going to go? We're going to go to the diagram. Right? Once the given has given up all of its information, and this one's done because it doesn't lead me anywhere else, we're going to go to the picture and ask ourselves, if I have 3 collinear points on a line segment, what's something I know has to be true about A, B, B, C, and AC in this picture? Okay, and so this takes us way back to Unit 1, right? And we are noticing that this is a segment split up into 2 parts. And we learned a lovely postulate that says that if we have 2 parts, that they have to add up to the whole thing. All right, so hopefully you remember what that's called, right? And so we can actually go ahead and write that algebra equation. I know without a doubt in this picture that AB plus BC has to equal AC. And I'm really hoping you remember that that's called the segment addition postulate. Right, that's from Unit 1. All right. So here's the fun part. All right, the given was great, right? But he didn't lead us to any other conclusions. The picture was awesome because he led us to this segment addition postulate equation. But he's a pretty basic picture, so I'm not getting anything else out of him other than that. So once you're done with the given, and once you've used up the picture, now you have to look at what you have, right? Now our next clue is going to come from looking at these 2 statements together and seeing if you notice anything, right? And something I really hope you notice is that these are 2 algebra equations, and both of them are equal to AC. And that's a really big deal. If I have 2 things that both equal AC, then doesn't that mean these 2 things have to be equal to each other? Right? If this whole expression equals AC and this whole expression also equals AC, then these 2 expressions have to equal one another. And that's going to be my next step. That AB plus AB has to equal AB plus BC because they both equal AC, so they have to equal each other. Now, I would actually take 2 different reasons for this. Technically, you could say that this is the transitive property. Transitive property of equality, because AC is my middleman. I know I told you that that transitive property can't have a plus sign, but I meant that it has to have equal signs. Like if this is equal to this and this is equal to that, then those 2 things are equal to each other. So we're looking at those expressions as like one whole quantity, that AB plus AB. So you could say the transitive property, or because we're in the land of equality, you could also say the substitution property if you wanted. Because technically, right, if AC equals AB plus AB, then wherever I see another AC, I should be able to substitute AB plus AB, right? So technically you are substituting as well. So either one of those would be appropriate here. All right, and then next up, remember our goal, I should have mentioned this earlier, we should always look at the proof statement. I totally blew past it. We're trying to get AB equals BC all by itself. AB equals BC. Well, looky here. AB equals BC. So we have everything we need. We just have too much. So you'll notice that we've got to get rid of the ABs on both sides. Well, we know how we can get rid of ABs on both sides. We can subtract them away because they're the same term. So if I take the AB and subtract it from both sides using the subtraction property, then that is going to give me the proof statement that I want, and we are done. We didn't even need all 8 steps. We did all that in just 4 little steps. Okay, so that's just our first of many geometric ones. That's a nice short one just so you can kind of see how that works. Tomorrow and the coming weeks, we're going to be doing tons of these. Okay, so we're going to get lots and lots of practice. Okay, so work on your homework, do the best you can. Try not to look at the answer key and kind of struggle through the proof yourself and try to figure it out multiple times before you go and look at that key. Okay, the struggle is good. All right.